on the design. Much more complex because it's multivariable, okay? Much more effective because it's relying on everyone's initiative and talents. A much more sophisticated design. Then I take that same design to my friend the Pharaoh. And he says, "What are you, a saboteur? What are you, a lunatic? What are you, a radical?" Whether or not a design is viable is not simply a technical or an economic matter. It's a political and cultural matter, okay? Let me give you one more example. I talked about de-skilling. An engineer falls in love. It happens. The engineer is a man, because most engineers are. He falls in love, in this case, with a woman. His girlfriend is about to have her birthday. This is an ace mechanical engineer. Okay, he goes to sleep dreaming about the perfect machine. Now he's beginning to dream about other things. It's starting to worry him a little. Anyway, his girlfriend is having a birthday. He decides to give her a present, and what kind of present could he give her that's most expressive of him? The perfect machine. He works for a week, designs this machine, wraps it up, puts a ribbon on it. The birthday comes. "My darling, happy birthday. This is a labor of love. This machine is perfect. It is so perfect, it can be run by an idiot." Your relationship is suddenly in doubt. She reminds him forcefully that she's not an idiot. And she says, "Take your machine or go back and redesign it for a not idiot." He's troubled because he had used the most sophisticated engineering principles that he had learned. Okay. The best machine is one that can be run by an idiot because of the imperative for de-skilling. Okay. So he goes back and tries to design a machine for his girlfriend for a not idiot. He looks through all his textbooks, not a clue on how to do that. His girlfriend suggests, "Why don't you pretend that you're designing it for yourself?" Good idea, because he knows he's not an idiot. Now, there would be a revolution in technological design if all engineers had to run the equipment that they designed for 5 years. Now, what I'm talking about is rarely articulated. And I'm trying to make it, these values visible by changing the context. Engineers don't talk about controlling workers. They don't talk about cheapening labor. They talk about reducing human error. They talk about eliminating the potential for error, closing the system. They talk about the elegance of the system. There's this idea of eliminating human error, very cynical idea. I mean, the idea that if a human being intervenes, it would be an error. Okay? Rather than, oh, a human being is intervening. God, the capacity for creativity, for enhancement. No. Human intervention is danger of error. So the language disguises what's really going on. In addition to these ideological habits of engineers, which are inculcated in engineers, and so they don't have to think about who they're working for or the values that they're subscribing to. It's never articulate. They have some drives of their own. This imperative for a closed system, reducing human error, reinforces and complements, dovetails with employers' concerns. All of these values and assumptions are also reinforced in what I call the sandbox of engineering, that is the military. You know, when you want to make something, let's say you're building something in the basement, and then someone calls, okay, it's time to go to the movies, or dinner's ready, you know, and you say, hey, wait, I have to see if it'll work. Okay. And you stop eating, and you stop going to the bathroom. You're just fixed getting this thing to work. Okay. And someone says, listen, it's time to, no, I've got it. You're working on your car, you know, I know I've got it now, you know. And you get into a kind of drive that you would kill to get this thing to work. Okay. Which is what most engineers do, that they go to work for the military, which is in the killing business. Okay. Because the military indulges this enthusiasm more than any other institution. The principal values of the military with regard to technology are performance. The military is charged with missions, and the priority of the military is to achieve the mission, and so you have to perform, and machinery, first and foremost, has to perform a function, regardless of cost. And we know what that means in terms of budget problems. And the second value of the military is command. And if any of you have ever been in the military, you understand what that means. Okay, it means I do, I say, you do. Okay? And no ands, ifs, or buts. And this is inherited from the church. It's a God-given right to command. The imperatives of the military reinforce the imperatives of the employer. Okay, now let me just very quickly go through this example. Okay. Reminding you that all technological alternatives are not born equal. Okay. Some, at their creation, are given preference by the political culture, while others are denied without a hearing by that political culture. Again, this is not simply a matter of technical or economic viability, but a social or political or cultural predisposition. Most of the technologies we have were never really tested for their technical and economic viability until after the decision to go with them was made and the social investment was made. And then they were belatedly rendered more or less viable. And when you come up with an alternative and say, what about this? They say, oh, that won't work. Or that won't be economic. Okay? And you're burdened in a way that the preferred technology is never burdened. Okay? A machine tool is the guts of industry. A machine tool is a machine that is used to form and shape and cut metal. And it's unique among machines because machine tools can be used to make machine tools, whereas you can't make a car with a car, or a refrigerator with a refrigerator. But you can make a lathe with a lathe. Okay. Machine tools are universal machines, general purpose machines. A lathe, a milling machine. These are machines that, depending upon how they're set up, depending on how they're operated, can be used to create an infinite array of products. They're universal. Some time ago, machine tools were automated, and what this meant is the universality of the machines was sacrificed. And these are called special purpose machines. You know about the auto industry. They change a car design, they have to retool, which means they have to chuck the machines that stamp out the parts, okay, chuck the tooling and fixtures that enable them to cut 1 million crankshafts, okay, and design new machines. So they're not universal, they're fixed. The task of automating machine tools came down to the task of what's now known as programmable automation. How do you make a machine automatic and at the same time retain its flexibility? And in some machines like turret lathes and others, this was done ingeniously with gears and mechanical devices, electromechanical devices. In the 1940s, this came to a head with a whole array of new technologies in servo mechanisms, electronics, which made it possible for the first time to really think creatively about automating universal machines by creating programs for the machines, letting the machines remain the same and just changing the program to change the part, something we're all familiar with now. Okay. So, for example, you have a universal machine, you have a set of punch cards that instruct the machine to do this series of operations. When you want it to do something else, you don't change the machine, you change the punch cards. Okay. Programmable automation. Now, what you have to understand about machining is that up to this point, precisely because machine tools were universal, the machine shop was labor intensive. If you're making 1 million crankshafts, you can afford to have a single-purpose machine because you're making millions of parts, and the volume of your sales offsets the cost in fixed capital. If you're just producing what's called a short run or a small batch of product, you can't afford to build a special machine for each one. You're making 50 of these, 100 of these, 300 of that. Programmable automation was seen as an answer to this. Up to this point, machinists ran the machines, machinists ran the shop, and machinists threatened the relationship of employer and employee. Machinists threatened the imperatives of discipline, of de-skilling, of displacement, through their individual power, through the fact that they possessed the skill to produce, and through their collective power through unions. The new technologies made it possible to perhaps change the realities of the machine shop by creating machines that are versatile yet programmable and eliminating the leverage of the machinist. There are two basic problems in designing programmable automation. First is the equipment to control the machine, so-called machine control. How do you make the parts move? That's relatively easy. The second problem, which was much more difficult, is you have the punch cards, or you have the tape. How do you put the information on the punch cards? How do you put the instruction on the tape? Where does that come from? How do you synthesize the skill of a machinist? The history of how that problem was solved reflects this array of values I've been talking about. First of all, the approach excluded labor completely from any participation in the solving of this problem. Management had exclusive control over the development of the technology. The first technology developed what was called record playback, or in a generic term is the motional approach. And it was just like it sounds. a person would cut a piece apart on a lathe, and the motions of the machine were recorded on magnetic tape and then played back. So the tape was produced by recording the actual machining by a human being and imprinting on the tape the motions of the machine, including the tacit knowledge of the machinist, who isn't really conscious of everything he's doing. Okay? He's responding to the machine, and that's all being recorded. And once it's recorded and captured on the tape, that machine can be made automatic for producing that part. And so instead of that machinist having to make 50 of these, the machinist makes one. That makes the tape. The other 49 are produced automatically. The key here is the assumption that the skill resides in the worker, the machinist, and that skill can be recorded. That's the approach. The repository of knowledge is the worker. Okay? There were a number of attempts to do this, rather successful in the United States and Canada. General Electric did some work, Gisholt, Warner and Swayze, but ultimately that technology never got anywhere. And I wrote a book, Forces of Production, detailing case by case what happened with all these. The money never came through, it was never pushed. Another approach to solving this problem came to be known as numerical control. Numerical control is simply this. Instead of assuming that the repository of knowledge is with the worker, the assumption is the knowledge belongs to management. And the knowledge of the machinist can be synthesized by management. Instead of recording an act, that act had to be formalized mathematically. The way this was done, you would take a part, mathematically represent the part, then go backwards and mathematically represent the path of a cutting tool over the part. Okay, it's called part programming. And in a very tedious and time-consuming process, formally create a program for every motion of the machine. Something that the machinist would do without thinking about it. Okay, now it had to be formally done. The computation that was required was enormous. And we're talking about the 1940s. Not only was it enormous, it was implausible. This is the technology that was developed. The cost comparison, there was no comparison. Record playback was infinitely preferable for 90% of metalworking functions in terms of its simplicity, in terms of its economy. Why was numerical control developed? Well, two reasons. One is the military. The Air Force, in particular, wanted to design particular products for high-speed aircraft, integrally stiffened wing sections, very complex dies, and they wanted a technology of machining that machinists couldn't really do beyond the capacity of a machinist. Even though that only amounted to 5 or 10% of metalworking requirements, this became the dominant technology because the Air Force invested a huge amount of the social surplus into it. Another reason was because the man who developed numerical control went to MIT for help. And the people at MIT didn't know anything about machining and couldn't care less about metalworking. Okay? They cared about computers. And at the time they were developing high-speed computers, and they said, this technology is fantastic. Look at all the computation that's required to do this. And they spent 15 years developing the most sophisticated machine for 5-axis machining that couldn't be used. It's like watching a discotheque if you watch it in operation. Beyond the range not only of mom and pop job shops, but 90% of the metalworking industry. And they indulged their enthusiasm for computers and computation and sophisticated technology. And the end result was a monster that no one would touch. It was over-sophisticated, and that means unreliable. It was a joke. And it was ridiculously expensive because once you had the piece of machinery, you had essentially furniture unless you had the program. And making the program, it turned out, it took 20 years actually to realize this, how difficult it was to make those programs. So people would spend $500,000 for a machine and then have essentially a piece of furniture because they couldn't get it to run because they had no programs. Okay? All the problems that were anticipated from the beginning. Okay? How then did the technology take off? It didn't. Except insofar as it took flight with the Air Force. There was no market whatsoever for this technology, so the Air Force created a market. And they said to the aerospace industry, we want you to buy these numerical control machines, and we'll give you the money to buy them. And they said this when there was only one in existence. So the aerospace companies now had public monies to give to machine tool manufacturers to develop numerical control. Now, once numerical control was developed, people had long forgotten about record playback and motional technologies. Okay? And people said, wow, this is the latest, best technology. And then historians look back at record playback and other technologies and they said, I wonder what was wrong with those technologies that they didn't develop. And people say, well, they really weren't that reliable, and they weren't economic, and they weren't technically viable, all of which was false. Now, when we get back to the capital-labor relationship, why did this new technology appeal to management? Numerical control took the control of the machine off the shop floor and put it in the office. Numerical control enabled management to control the workforce, control the pace of production, discipline its workforce through the machine. Taylorism on tape, they call it. Earl Troop, who was one of the people who was involved in the technology of General Electric, they shifted from record playback to numerical control. He said, look, with record playback, the control of the machine remains with the workers, the people who make the tapes. And the unions can bargain. This is our function, because it's essentially machining. With numerical control, the control shifts to management. And as Earl Troop, who was a manager, said, and why shouldn't we have the control? There are machines. Numerical control also meant that management could de-skill the workforce. That is, building the intelligence of production as much as possible into the tape. Now, in their enthusiasm, they ran away with this quite early. They thought that machine operators could be just monkeys. It didn't turn out that way because the machines were so unreliable. Unless you had a skilled person working the machine, it was a disaster. But that was the assumption. By de-skilling the person, it meant you could cheapen the operator. And in the first decade of the introduction of numerical control, management everywhere tried to lower the rates for machine operators. This became a major political battle. Finally, numerical control enabled you to displace people. You could now produce more on one of these machines, And so you could get rid of some people. It didn't mean that the people who were still there were now relieved of burden. It now meant that they ran 2 or 3 machines rather than just one. It didn't mean they had more leisure, because the expense of these machines required that they be run 24 hours a day. So the shift system was changed, so that the weekly time of work was now 50 hours rather than 40 hours. This technology appealed to the military for the reasons I've already suggested. The military, as early as the 1960s, the Air Force had fantasies of a manager, supervisor coming into the factory, taking off his jacket, and going into the microphone and saying, orders to the plant, drawing a part, and then reading the specifications of the part into the microphone, and then it goes automatically to the machines, and everything's done, no human beings whatsoever. And not only that, but the factory didn't have to be right here, it could be on the other side of the globe. This has turned into a reality, of course. Complete and total command. Now, when this was done, there was great concern over the radical labor unions and the potential to eliminate any intermediary, any human intervention in the process of production. It was deemed essential for military logistics. If you know the history of the longshoring industry, it was the Navy who came up with the idea of containerization to eliminate the longshoremen, because during the Korean War. Finally, the technology appealed to engineers. It was elegant, sophisticated. It eliminated human error, meaning the error of people on the shop, and it afforded them total control. So the next time you're in a factory and you look at the machine tools, they're all Japanese, by the way, because US machine tools don't work. They're too sophisticated. You look at the machine, look at it closely, and you think about these things, it'll all become obvious. The control cabinets are locked. If you ever run a Xerox machine, you have 99 pages to Xerox, okay, and you get 98, and then the machine goes down, right? And a little light comes out, add dispersant, right? And you say, oh, great, and the cabinet's locked, of course. It says, see key operator. And then you run down the hall and the person's out to lunch, right? So the Xerox machine, a very sophisticated piece of equipment, is furniture, right? Now, if you had a key, or if the cabinet wasn't unlocked, you could use this incredible capacity to add dispersant, right? Well, if you're on a shop floor and you're running one of these machines and something goes wrong, the chances are you know how to fix it. But in many factories to this day, if you're caught with a key to the cabinet, you're fired on the spot. Again, like my boss, Mr. Masters, sir, the relationship has to be maintained. Now, let me close in a rush. I'm sorry to have gone on so long here, by talking a little about another dimension to this, which I'll be happy to talk about in questions. The economics of technological development in industry is very ambiguous. The idea that automation is economic is, as I say, ambiguous at best. The rush for automation has as much to do with the status consciousness of purchasers and the enthusiasms of managers and fears as it does with any genuine economic viability. And you might know that many industries, especially in auto, are backing away from automation because it's economically problematic. But I've been trying to understand for a long time some of the underlying compulsions, and in this book, Forces of Production, that was published in 1984, and I'm drawing a bit from here and talking about numerical control, I was left unsatisfied in that study that I really hadn't gotten a handle on this. And having worked at MIT for 9 years, I'm in another technical school now, having been at the Smithsonian for a while, I was very familiar with the culture of engineering, the culture of design, and I was convinced that something else was also going on here. Something else having to do not only with the fact that the people who have the power to design this technology are not only management, but they're also male. I've just finished a book called The World Without Women. It's the clerical culture of Western science. And it covers 2,000 years of how the culture of science was created out of essentially the culture of the church, a celibate, homosocial, misogynist culture. The title of the book, A World Without Women, suggests the nature of this culture. It's an all-male culture. The question, when you ask the question about class, how does technology reflect the relations, class relations, which I've tried to explain a little. Similar questions can be asked about, I don't like the word gender, but let's use it. What does it mean that all the designers are male? Or 99.9%. I used to be a curator of automation at the Smithsonian, and I'd go around and say, come on, let's correctly label these exhibits. I mean, this is a male laser, this is a male lathe. Everybody would laugh. If you said this is a French or this is a German, that's fine. But if you say male, they'd laugh. What are you talking about? Okay. Then I put together an exhibit called Automation Madness, Boys and Their Toys. And everyone knew what I was talking about. You say boys and their toys, and everyone knows what you're talking about. Of course, boys and their toys. Okay. The question is how to get at this in a more sustained way rather than just metaphorical. Well, one thing I learned in this World Without Women book is that a culture in which women are not present exaggerates perhaps an already existing tendency in men to appropriate, simulate procreation. That is the function that's absent. Groucho Marx, he's on an elevator and a priest walks in the elevator and the priest says, "Aren't you Groucho Marx?" And Groucho says, "Oh, yes I am, as a matter of fact." And the priest says, "I have to tell you, Groucho, my mother loves your movies. She thinks you're really a genius." And Groucho says, "Oh, really? I didn't know you fellas had mothers." It's a very penetrating joke. Because a world without women is a world without mothers. And metaphorically, the mother church and St. Bernard used to talk about his lactating, and Jesus insisted on being called mother, and St. Francis. I mean, there's a long history of this. Okay. What we find coming out of this culture in an exaggerated way are efforts, as I said, to create life without women. You've probably heard of the homunculus, efforts going back to the Middle Ages to create human beings without women. Have you ever heard of that? The homunculus? Paracelsus, the 16th century alchemist, had a recipe for it. You take semen, you put it in horse dung, warm horse dung, for 40 days, and you fertilize it with the blood of this and that, and after a certain amount of time, you will have a little person, okay, known as the homunculus. And if you nurture it, it will grow up. It will be shorter than most human beings, but smarter, okay. Now, the homunculus was taken very seriously throughout the Middle Ages. Von Leeuwenhoek, in the 17th century, the inventor of the microscope, one of the first things he did was look at sperm, and one of the first things he saw was, there's the little guy. Okay. So this is a never-ending saga to create human beings without women, and of course it's still going on. If anyone believes that artificial reproductive technology has anything to do with helping infertile people, I suggest otherwise. Okay, this is an effort to create human life without women. Another aspect of this, and very much related to it, was a fascination with the simulation of life, or what's called automata. In the 10th century, Gerbert, or Pope Sylvester, created a talking head. Albertus Magnus, Roger Bacon, Robert Grosseteste, some of the giants of the medieval intellect, Arnold of Villanova, all produced automata, that is, life-like beings, using the latest technology at their disposal. This effort peaked in the 18th century with advances in mechanical, especially clockmaking, mechanical technology, pneumatics, hydraulics. And you had these ingenious devices which were made for the entertainment of the royalty, chess-playing turkey, piano players, flute players, a boy who writes, and perhaps some of you have seen these automata in museums, okay? Ingenious, and with a premium on their lifelike appearance, okay? The simulation of life. The premier automata maker was Jacques Vaucanson in the 18th century. He made a flute player, made a tambourine player. What he aspired to make most of all, he also made a duck, his famous duck. Maybe you've heard of the duck, which was the digesting duck. It would eat and excrete. Vaucanson's pet project was the construction of a human being, an android, which would have all of its functions, the circulation of the blood, respiration, digestion, okay? But because of the complexity, he never quite finished it. Now, Vaucanson is known to us for another reason also. Vaucanson was one of the pioneers of industrial automation. Vaucanson was the head of this commission on silk manufacturing and developed technology which was the precursor to the Jacquard automatic loom. And in fact, his technology was burned and his life was threatened for the introduction of this technology. So in Vaucanson, you have the compulsions to automate on behalf of employers and the compulsion of men to simulate life combined in one person. Are they so far apart today? If you go to the National Bureau of Standards, where they develop robotic systems, you see people, the way they handle their robots. I mean, there's something very nurturing about it. James Lighthill is a Cambridge University mathematician who incidentally holds the chair held by Newton and also held by Charles Babbage, who was one of the pioneers of computer technology. He was asked several years ago to do a report for the British government on artificial intelligence. And to his credit, I mean, it took some courage, his report included this passage. It has sometimes been argued that part of the stimulus to laborious male activity in creative fields of work, including science, is the urge to compensate for the lack of the female capability of giving birth to children. If this were true, then building robots might indeed be seen as the ideal compensation. The view to which this author has tentatively come is that a relationship which may be called pseudo-maternal comes into play between a robot and its builder. In just about every so-called primitive society, anthropologists have documented the universality of what are called couvage or couvade rituals. These are rituals whereby the men of the community ritually appropriate the act of giving birth. The woman goes into the woods, has the baby. The men, through a very elaborate and genuinely experienced, this is not mere play, ritual, act out childbirth, screaming in pain, and going through all the exercise of the act. This is called couvage. An effort by men ritually to appropriate the one function in which they have not become dominant. I'll say yet. Is automation the couvage ritual of industrial society? I'll leave you with that thought. Thank you very much. I'd be happy to answer any questions of those who are still here. Yes, sir.